Good evening, everybody.
Welcome to all the participants for the third day of this FDP. We are delighted to welcome the esteemed speaker, Mr. Ashish Bhutani, sir, the Director of Sterling Cryogenics India Limited, New Delhi. Mr. Bhutani is a distinguished professional in the field of cryogenics and low temperature technologies, leading one of the most trusted companies providing the advanced cryogenic solution across India. With extensive experience in delivering the high-quality liquid nitrogen system and pioneering cryogenic innovation, he has played a key role in supporting the sectors such as research, healthcare, industries, and emerging energy technologies. Under his leadership, Sterling Cryogenic India continues to bring the globally proven cryogenic expertise to the Indian landscape, ensuring the reliability, efficiency, and technological excellence. We are truly honored to have, sir. Yes, sir. Welcome, sir.
Hello.
Hello, sir.
Yes, sir. Yes, sir. I'm listening,
Yeah,
sir.
yeah.
Yes, sir.
Yes, yes. You are also audible, sir. No problem.
Yes, sir.
Yeah, yeah.
Thank you, sir. Thank you so much for such a decent opportunity and such a warm welcome and introduction. Uh, it gives me great pleasure and contentment that I am glad that I am today presenting about myself, about my company to the eminent faculty members of Army Institute of Technology. I sincerely and wholeheartedly thank you for giving this glorious opportunity. Let me start with my brief introduction. The thing which most of you have said, but मैं इतना बड़ा आदमी नहीं हूँ. I'm like a normal human being like you, sir, and I really have high regards and gratitude towards my professors, to my teacher, who has really instilled good values and education. Uh, my name is Ashish Bhutani. And I was born and brought up in Jalandhar, in one of the city in Punjab. My entire schooling happened over there in Jalandhar. And then since I became little bit of serious into my 12th, so I got a chance to crack the AI Triple E and get the chance to study at REC Kurukshetra, our Regional Engineering College, which was then in 2002 converted from REC to National Institute of Technology. Since I'm born and brought up in a middle class family, so hard work with commitment and passion is one of my driving factor. So because of the hard work, I became the class topper, college topper, and then eventually the gold medalist in my engineering. I passed out in the year in the 2005 with the gold medal onto my neck and started my first journey with the ABB. Asia Brown Boveri as a graduate engineer trainee. And over a period of time, then I moved into renewable energy. I was into Maharashtra also, Satara, wherein we commissioned 45 megawatt of renewable energy project. 45 megawatt is not a big number, but by virtue of that, there was a huge gap of almost 6 years. So the at the age of 25, 24, which I got commissioned with my team, I always believe in teamwork. And because of that, we commissioned 45 megawatt, and the management was very happy. They were satisfied, and they asked me that what you want. I have never aspired to be a millionaire or to be a director and all those things. I always believe that you do your karma, that thing will come back to you. And I asked for the transfer to Delhi, moved to Delhi, and then started looking around the projects financially, how to raise equity, capital, and all. And then I worked with Inox also in Gujarat. We commissioned 450 megawatt of project before landing into Sterling Cryogenics. Being a mechanical engineer, gold medalist, so that was my passion. That whatever we have studied in our mechanical engineering, all of these cycles, thermodynamics, Carnot efficiency, Stirling cycle, Gifford McMahon, Joe Thomson. So then I thought that this is the right company to work for that whatever we have studied, we will experience it. So I'm going to run my presentation, which I'm sure that you will like. And all of us are mechanical engineers or engineer, so I'm sure I can use any terminology which will be easily grasped. I always give this credit to my professors, to my teacher, and I always go to back to Sharda, and the philosophy is very clear that whatever we are today, I am today because of professors. So I will not charge even a single penny to give my lecture. And if even if I have any kind of busy schedule, I always make sure that for this I should give the priority to the society to this. So this is what I can say that as of now I'm doing this CSR activity. Yeah. So I'm going to run and I have my team also with me. Simran is there and Pinky Verma is there. She's taking care of process coordinator. Simran is our R&D department, and we do have Mr. Rahul Rangar, who is our head of the R&D department, and many other team members are also part of this session. I welcome them also to this forum. So allow me to run the presentation. Today we are going to cover that what is Sterling, how we have revolved, and what is our contribution into hydrogen refueling. So I'm sure that you will really appreciate the presentation which my team has prepared. Whether my screen is visible to all, or I need to do that, I believe.
Yeah, you need to share.
Yeah, yeah. I think it's visible now.
Yes, sir. Yes, sir.
Great. So basically, Sterling and Fabrum. So Fabrum is a New Zealand-based entity which was incepted in 2004. So Sterling is the name of, as you know, that Sterling is the name of one of the scientists, Robert Sterling, who has invented heat engine in the year 1816, 18th century. So basically, the name of Sterling has been derived from that very scientist. So once again, I thanks all of you to give me this opportunity. So I welcome all of you to run through my presentation and my company profile. What I'm going to cover the company profile, what are the key products and services we do, what is the history of our company, what is our USPs and global trend, what we are doing R&D and all, projects what we have done, what is the future plan. So this is what I'm going to touch along with the hydrogen refueling station. And I'm sure that you, next half an hour, you will really enjoy the journey, which with the passion which I still have as a mechanical engineer. So basically, the this is our journey, this is our growth that we have. We have the name which is from the Robert Sterling, who has developed a hot air engine, and we do exactly the opposite. We do not create any heat; we create the cooling power. So 1937, we started working onto this cryogenic technology. It took us almost 8 years and then 10 years to develop the first prototype or first commercial project. That is what we always say that we have launched our first commercial product, which is under the Philips, which is known as PLN, Philips Liquid Nitrogen. So that was the in the 1955 we have launched our the market capable, the product suitable to the market, and that we have done. You must have know the department which is Anand, that Amul Dairy. So Dr. Varghese Kurian, who has brought the frozen cement technology, he was our first client. We gave two machines on a free of cost basis, and then he gave us a lot of orders. So all of these frozen cement technology, we say proudly that our role was also impeccable into that because we stored liquid nitrogen, we produced liquid nitrogen, all of these semen sample, all of these straws and all have been stored into that very liquid nitrogen. And by virtue of that, the India has seen that now India is number one into milk production. So the onus goes to Philips also, to cryogenics also. So that is the real strength of cryogenics. In 1990, in 90, sorry, 2002, after about 47 long year, Philips has sold off all the assets, liabilities, customer base to Sterling. And since then, we are working under this brand name, Sterling Cryogenics. So we are, and as I started, and in 2005, we have sold 5,000 machine worldwide. And now we have almost about 18,000 machine in the entire world. So we operate pan world and we operate pan India as well. So in 2014, I started my journey with Sterling as a senior manager operations. 2015 January, I became one of the director, and 2019 I got the entire stake of Sterling India to become a fully independent Indian organization. And by virtue of launch of Make in India, we are the first company who has developed, who is the class one supplier, wherein we manufacture 50% of our cryogenic system over here in India. And in 2022, we have expanded our footprints to the green hydrogen and all. Recently, that Mr. Nitin Gadkari, who drove from his first hydrogen-driven car, which is known as Toyota Mirai, so that very storage container that was developed and fabricated by us and by our principal company. So that is the thing which we are proudly doing. India is still to experience a lot of transformational gear to the towards hydrogen, and we are the forefront into that. Next is, so this is what our one slide that we have 70 plus years of global legacy. We have installed more than 700 systems all over India, and we are Make in India a company, that we are the first company who has adopted this Make in India concept when it was launched in 2020. So allow me to run a small video about Sterling.
Sir, we can't see the video. Sir, we can't see the video.
Oh, so uh, should I run it once again or? Mm,
You try for once.
okay, okay.
Complete
Mm,
screen share, presentation share. You need to share complete screen, then only we can see the
yes,
video. Yeah.
yes, I think so. Yeah, you can.
So, okay.
Is it okay now?
Yes, sir. Yes, sir.
Is it now you can see the video?
Yes, yes, sir. Yes, sir.
Okay. you, sir. Uh, Now I'll move to the other slide. So we Sterling. Uh, so basically, we have four pillars. Cryogenic is our main forte, wherein we liquefy nitrogen, oxygen, liquid air, LNG, and hydrogen as well. Green hydrogen is our new venture. It's a niche market as of now. We are working with Indian Railways. We are working with Toyota for the development of special types of container, which I'm going to present in my presentation today. Third vertical which we have is industrial segment, wherein we manufacture our own chillers, right from 2 ton to 60 tier. We promote German brand Compare. We promote US brand Parker, and we have our own small hydrogen, nitrogen, and zero air generators, which are predominantly into any labs. Last but not least, since I am having 10, 11 years of experience in renewable energy, so renewable energy is our fourth pillar of innovation. So these are the basic verticals of Sterling Cryogenics India Private Limited. So if I move to, so we are having a collaboration with Fabrum, which is a New Zealand-based company started in 2004. Fabrum is also a very, very decent company to work with. So we were the first company who has basically handshake when the launch of Make in India was announced, which I'm going to share in my presentation. Allow me to run a brief video on the Fabrum also. Screen is visible, video is okay.
The screen is visible, sir, but we
Yeah,
can't hear. That is, audio
yeah.
is not. Yeah.
Now
No. Audio is not there.
audio is not.
Yeah.
So can I do something internet? Uh, I'm sorry that the video was playing, but you can't hear the background music and the background sound. So I'm sorry for that. But
It's all right, sir. It's all right.
I'm sure that I'll be able to cover the journey. Basically, Fabrum is a Latin word which means smart manufacturing, clever manufacturing. So that is what we really do. Uh, we do have collaboration with Fabrum for the cryogenics solution and for the green hydrogen. So we present the solutions and we also do our own research and then propose the solution accordingly. So you will be really astonished to learn that Indian Railway is coming up with the first green hydrogen driven engine. right? Their trials are underway from Jind to Sonipat, which is about a 90-kilometer stretch, and they are running that engine on the green hydrogen gas. So we are in active discussion with the Honorable Minister Vaishnav ji as well as with the Minister of State Ravneet Singh Bittu ji to propose the liquefied version of hydrogen. So once you liquefy the hydrogen, it's not an easy task, and you store it, which is rather not an easy task. But once you do that smartly and with a lot of R&Ds and all, so you really save a lot of substantial saving is there into the volume and into the reliability enhancement. Gas can catch fire, but liquid doesn't. So that is what we are proposing to the solution to them. And this is something which we are sure that it will be a great breakthrough. The way we have breakthrough with Toyota Mirai, wherein we are now manufacturing for them the storage containers which is used for the automobile sector. We are also working with NTPC for their NTPC Netra for their green hydrogen solutions. So Fabrum is 21 years of experience company that we do have patent around our cryogenic solution. This is the only organization in the world who has dual patent onto the cryogenic technology and onto the green hydrogen solutions. So our key shareholders are Fortescue, K1W1, Obayashi, and AP Ventures. So Fortescue is a big company in Australia. Their vision is that by 2030 that they will have their own mining operations wherein entire fleet of their trucks will be converted from diesel to green hydrogen. So we are actively working into that. In fact, we have put up the couple of projects with them at Australia, wherein we have given the concept to commissioning solution to them. So that is what we do. And Fortescue is like, if I tell you about in Indian perspective, so they are the Ambanis of Australia. So this is our core competencies. We are into cryocooler, like liquid hydrogen, liquid oxygen, boil off gas management, electrolyzers, biomethane, and liquid nitrogen. So that is our cryocooler competencies we do have. And in composites, if I tell about that, then we are into aviation, for which we have developed these kind of special containers for aviation sector. We are into heavy transport. So this is the real photograph which we have put up the project in Christmas Creek in Australia, and then magnetic and superconducting applications customs based. So we do not only push the solution which we have, we understand the customer requirement and develop the solution accordingly. And that is what we really have the core expertise. Like if I tell about the Indian perspective, we have had carried out projects with IPR, we have had carried out projects with BHEL, we have carried out projects with NPCIL, we have carried out projects with Bhavini, wherein we have not only promoted our standard product, we have understood the requirement of customer and then proposed the solution accordingly. So these are our main functional divisions, that liquid nitrogen, liquid oxygen, liquid hydrogen, boil off gas management. Boil off gas management is also a new niche segment wherein we are we are putting up the project, we liquefying the gas which is coming out and reducing the losses. It's basically a zero loss system. In hydrogen refueling, we have developed 1 megawatt and 5 megawatt fuel station. We have put up 5 projects in Australia so far. And composites, so this is a liquid hydrogen storage, and this is a real photograph that he is our technical director who has actually hold the hydrogen storage container in his own hand. So we have developed very lightweight hydrogen storage container that can be used for aviation and for other sectors. So our vision and mission is very clear that we would like to be a world-class manufacturer and service provider, and we would like to be a one-stop solution for industrial and green hydrogen requirement. And mission that this is what we are doing from last 70 years. If it's cryogenic, the first name which should come should be Sterling India and Fabrum. So that is what our mission and vision, and myself and along with my entire team, we work day and night to make sure that our vision and mission is absolutely ensured. So cryogenic solutions. So our solutions goes into animal husbandry. We have more than 50% of our customer base into all of the India animal husbandries. You name any IIT, you name any NIT, we do have presence over there. State universities, central universities are our main clients, medical line, pharma, IVF center, research labs. So our cryogenic solutions goes very well into these critical sectors. And this is our product range. We are into from small to mid range of product. We are developing 1.5 liter per hour machine for which Mr. Rahul Rangar, who is our R&D head, along with Simran Chauhan, she is also over into R&D. So they are working day and night to make sure that this product is launched by December 2025. The new year we should have been this product, and that product we are developing indigenously on the GM cycle, Gifford McMahon cycle. So 1.5 liter per hour to 100 liters per hour. That is our main customer and product range. So we have almost 750 plus plant all over India. So this is what the change which we have experienced way back in 2020, that when Prime Minister, Honorable Prime Minister Modi ji has launched Make in India and Vocal for Local and Local to Global. So we have all these air compressors, the receivers, the PSA, the voltage stabilizer, and the chillers, and the entire gas part is developed by Sterling India. And from with the Fabrum, we have cryocooler and panel. So these two components are getting manufactured. So our discussions are underway with Fabrum that why not we manufacture the entire system over here in India. So very soon, within the next 1 year, we will have that kind of setup in factory wherein we will manufacture the entire system over here in India, and that is going to be a breakthrough journey in the history of cryogenics. And these are the standards which we follow. We are 9001 2015 quality management system. We are 14001 2015. We are 45001 2018. And we are CE certified. We are Udyam company. And we are also registered with Z, zero effect, zero defect, which is a bronze category. So that is what which is honored by Ministry of Small and Medium Enterprises. So we follow the highest standard. We do not encourage. We do not have any kind of a system which doesn't work and all. We do rigorous R&D. We do rigorous testing before dispatching the system to any of the client. And this is something which is very, very important for us as a mechanical engineer, that we have developed this patent technology. We have dual patent, long life, and DPWG, diaphragm pressure wave generator. What is basically, this is basically a hermetically sealed compressor where the expansion of helium and the compression of helium takes place into these small cryocular tubes. So basically, this is a pulse tube technology. And by virtue of that, since there is no moving component, so this has the relatively longer life, higher reliability. That is what we proudly say. Once you have our product, so then for next 10,000 hour or 12,000 hour, the machine is running continuously. So you do not require any sort of maintenance. After about 10 to 12,000 hours, the only two filters are required to be replaced, and only the hydraulic oil which is there into this oil reservoir, so that needs to be replaced. So this is the beauty of our technology, that is why we have written the patent, we have established the standard, and we have followed that. So that is what we proudly work into that. And this is the erstwhile technology, because I always believe that continuous improvement is the life. Kaizen we follow. So this was the third generation machine wherein that the piston and compression takes place in this compression space. So we have, since we follow the Stirling cycle, so we have the similar technology, but we do not have the actual movement. We do have the virtual movement, and that's the diaphragm which we have developed in that way, that it is basically giving the longer yield or longer reliable life of the system. So that is what we have changed, that this machine used to be maintained after about 6,000 hours, and we do not require the maintenance till 12,000 hours. And major maintenance used to happen over there in this technology is about 16,000. So in this we have experienced 40,000. The patent states that the major maintenance happens at about 40,000 hours. So if I calculate in number of years, if the machine is installed today and it is running around the clock, say about 8,000 hours in a year. So for next 5 years, we do not require the major maintenance. So that is what we have given. But when we have actually tested, so we have tested this machine for 7, 8 years before launching into the market. So we have experienced that this diaphragm, which is there into this space, so that has actually crossed more than 50,000 hours without failure. So that is why that we have been honored with these two patents. And these are the preventive maintenance schedule which we follow. The major strength of our company is the after sales service support, and we do not only proudly take the longer warranty because we know our product, we know our team. So we also after completion of warranty, we enter into a long-term service contract, 3 years, 5 year, or even 10 year. So that is what, and our service engineers are very trained. They keep on getting the training onto the various new technologies and all, and uh, and they render the services on pan-India basis. Not only in India, we also depute our engineers to the foreign country to do the installation job, to do the preventive maintenance, or to do the corrective maintenance and all these things. So that is what our major USP, that after sales service is very crucial for us. So coming back, so these are the projects. I have not highlighted the entire 700 plus system. I have specifically stressed out onto those projects which we have executed after the launch of Make in India. And I'm really proud and I'm really glad to work with this company, that we were the first company who has been awarded with the first product project when the Make in India was launched way back in 2020. So I've specifically chosen those projects which will really give a lot of insights about us. So this is a project which we have installed in Kargil at the minus 20 degrees Celsius temperature, Pasighat, which is about 100 kilometers from China border, and Ujjain. If any of you visited Ujjain next time, so you kindly visit our plant also, which is about 3 to 4 kilometers before the Mahakalji's temple. And this one project, it is one of the biggest project in the entire MP, and one project is catering to the liquid nitrogen requirement till Indore. So there are about seven odd major stations, 120 substations, where this liquid nitrogen one plant is fulfilling the entire requirement. So as I mentioned that this was the first project in the Rajmata Vijayaraja Sindhi Krishi Vishwavidyalaya Gwalior, and this was the project, and the entire management was very elated and felicitated us. And this was the first project in the history of cryogenics wherein we have manufactured the system over here in India, and we are still the class one supplier. And from that day on, we have never looked back. We have got couple of projects. This is through tendering, but we always get success. So this is the second project which we have put up in Kargil at minus 20 degrees Celsius. And that also, this very project was published into their coffee table book when this Leh was declared as one of the UT, which was earlier part of Jammu and Kashmir. And this plant is giving about 600 liters per day production. And that was the third project which we have done in NIT Warangal. And these gentlemen, they come over here, and our team also does work with them, and we showcase the united spirit. And this is one of the biggest project in the entire MP, which was inaugurated by Honorable Chief Minister, Dr. Mohan Yadav ji. And this is installed in Mahakal, a prominent tourist place. And this was the project which we have put up in Pasighat, which is in Arunachal Pradesh, which is about 100 kilometers before the China border. And NIT Rourkela, that is what we have recently put up. And these are the various, when Honorable Prime Minister of New Zealand was here in country, so I was also specially invited. and we have I have given him the symbol of Hinduism or the symbol of Hindu culture, the Bargat tree, so that we have a profound association. So this team from Inox was here, team from New Zealand was here, and that is what I have given presentation in the cryogenic conference at Tata Institute of Fundamental Research, and he is the professor at TIFR, Hyderabad. And these are the appreciation letters. So what we do, we always believe that every day is a new day. So appreciation letter gives us motivation, but it also fills us that tomorrow should be a better day than yesterday. So that is what we always believe in. And these are the products for the hospitals which we manufacture over here in Noida. I invite all of you to visit us and to visit our factory. So we have products from 20 bedded hospital to 400 bedded hospital. And these are the industrial projects like Compare, Garner Denver, Parker, and Vichy we represent for pan-India basis. And this is main the topic of today, green hydrogen. The future is this, because all of us are experiencing that the fossil fuels are getting depleted day by day. The prices of uh, petrol and diesels are increasing day by day. So the alternative solution has to be developed. So that is what we are proudly doing a lot of R&D, a lot of research, a lot of innovations, and also launching many solutions towards this green hydrogen. So basically, all of us know that there are three types of hydrogen: gray hydrogen, blue, and green. So why we say as a green? Because first and foremost, our entire system operates on the renewable energy. We do not use any fossil fuel or any natural gas, biomethane or anything. So that is why we proudly say that we produce a green hydrogen, which is basically depleting the carbon credit, which is basically giving the carbon credit. We are removing the carbon content, and also we produce a very clean hydrogen gas and liquefy that. So that is what the future is. That is it. It's into transportation, it's chemical industries, energy and storage, and liquefaction and export. So that is what we do, and all of us know we are all student, and at the age of seventh or eighth class we have done a lot of practical this one, wherein in one beaker or in glass of water we have put one cathode and one anode, and we could see with our naked eyes that the ions are getting dissociated. So this is the same principle of operation which we do, but in a different scale. That was a very small scale, but now we do it on a different scale. So we have two technologies. One is the proton exchange membrane, and second is a membrane-free electrolysis. So proton exchange membrane technology is also good, but that is good for a smaller, you can say scale. Like if I have to produce say 100 milliliter per hour to 1.5 liter per hour of green hydrogen, of liquid hydrogen. So that scale is good for PEM. That is basically proton exchange membrane, wherein there are cell which gives positive polarity and negative polarity, whereas in the membrane-free electrolysis, which we have the patent also into that, wherein we are producing from 450 kg of green hydrogen to 900 kg of green hydrogen. So that is what, and these are the various R&D projects. As I mentioned to the audience, that we are launching this very small, very compact system exclusively for IVF centers and for the nursing stations, wherein we will have the machine which is from 20 liter to 30 to 50 and 60 liter per day, exclusively on the GM cycle, Gifford McMahon. So these are the hydrogen generator which we have developed from 100 milliliter to 1350 milliliter, 100 ml to 600. So basically on the carrier grade, detector grade. So this is the product which we have in our in-house manufacturing for the small lab scale, which is on the PEM technology, proton exchange membrane technology. And If I tell you about since we are all engineers, so basically the difference between PEM and membrane-free electrolysis is very solid. First and foremost, the difference is that in PEM technology, if I have to produce 450 kg of green hydrogen gas, so I need 2000 parts per stack. However, if in this technology that membrane-free electrolysis, I only require 400 parts per stack. So as the number of parts are less, so the reliability of the system is more. And the second major difference is in PEM, we only use very clean water, distilled water and all. Whereas in membrane-free electrolysis, we can use any sort of whether dirty or dusty or any kind of water because that will be clean and the green hydrogen will be produced. So that is what is the major difference. And the cost of ownership of this system is comparatively less as compared to this. And we have two products like 1.1 megawatt, we say 1.1 megawatt unit and 2.2 megawatt. So 1.1 megawatt and 2.2 megawatt unit, the major difference is only a double. So whereas what we do that we feed 4050 kg of water in a day, and out of 4050 kg 3600 kg of oxygen is getting produced, pure oxygen, and 450 kg of green hydrogen is produced at a very high pressure, which is about 9, at 34 bar of pressure and at the purity level of 99.9%. Whereas in 2.2 megawatt, we feed 8100 kg of water and 7200 kg of oxygen and 900 kg of hydrogen is being produced. And these are all systems are self-contained. It is into a 40 feet container, and this is something from the right from electrolysis, then production of hydrogen, and then liquefaction of hydrogen. So that is what the entire system is stacked into this 40 feet container. So this is something the future that this is the project which we have put up in Christmas Creek at Australia, wherein we are converting all of their diesel uh, trucks into green hydrogen driven trucks, and that is what we have put up the electrolysis and then liquefier and then storage and all those things. So storage of hydrogen is not an easy task. If it is not handled properly, so it could turn into a hydrogen bomb as well. So what we have basically done that we have this technology that what we have done, every cryogenic container has to be a double wall, um, insulated, self-insulated. There should be a vacuum insulation in between. But in the case of hydrogen, to make sure that our systems are reliable, consistent, and perform, so we have developed triple skin hydrogen container. So even though it is triple skin, that one layer, second layer, and third layer, so the weight is not very high. It can be easily lifted with the on the lap, and also, this is the real photograph which for which we have done the project with Australian Prime Minister, his private plane that is actually on the green hydrogen, and for that we have given the solution. We have given the hydrogen storage solution to Australian Prime Minister. So that is, and also into the chase boat. Uh, Sorry that this slide is not. Yeah. So basically, explaining the yeah. So we have also developed the hydrogen storage solution for this chase boat, which operates at about 350 knots mile, and for that to achieve those kind of speed, so you need the entire system to be dynamically balanced, and it should be of lightweight. So that is what we have developed these. There are two hydrogen storage container in this, which has having hydrogen, liquid hydrogen, and that runs onto the hydrogen this one, and it's very lightweight. So these are the spare parts and after sales service. Since we also operate pan India basis onto a very various private customer, so they need the 24/7 support. So we have the fleet of spare parts around the clock available at our factory and at the strategic locations within country, so that our engineers can render the quickest possible service support. So our idea is very clear that we wanted to expand market share. We wanted to develop more and more solutions under Make in India initiative and focus on sustainability and green energy. And we wanted to strengthen our after-sales service upon the service. So I can always say that if we are having back-to-back repeat orders, so that all goes because of the service, the impeccable service support which we render. And these are the industries which we serve: medical, food and beverage, laser, electronics, gold mining, petrochemical, marine, power projects, biostorage, research, space and observatory, and that's all. And this is the observatory at Hanle, which has our own uh, liquid nitrogen solution, which is running there since last 2025, 26 years. Yeah. So that's all about the Sterling. Now I open the forum for the audience to ask any kind of a questions, please.
Sir, thank you very much for your session. It was
Thank you,
very
sir.
nice session. सर आप जब मैंने आपकी इंट्रोडक्शन दी थी तब आप बोले कि मैं तो बहुत छोटा इंसान हूँ, लेकिन आपने तो प्राइम मिनिस्टर, ऑस्ट्रेलिया के प्राइम मिनिस्टर का एरोप्लेन में ये लगाया है. दैट
Thank
इज
you, sir.
रियली फैंटास्टिक थिंग टू लिसन एंड सी.
Thank you,
इट्स हैट्स ऑफ टू यू सर.
Thank you, sir. Thank you so much. It's all the credit goes to my team. I'm whatever I'm today, it's all because of my team, sir. Yeah,
Okay. Yes, sir. Yes, sir. Sir, I have one question. If we
please.
compare the hydrogen vehicle with
Yes,
electric vehicle,
yes, sir.
how does it usually take to refuel the hydrogen?
Right. It's a very fantastic question. First of all, sir, that electric vehicles which are there in the market, and I'm absolutely they are very good, and but they are all into the lithium-ion batteries. They are all operate on lithium-ion battery, which has a specific lifespan, maybe 5 year or 10 year and all. And as of now, country has never experienced that after 5 years, how are we going to dispose of those batteries which will live up to their reliable lifespan? Whereas in the green hydrogen, it's a water. It's only a water which gets dissociated through technology and it doesn't create any kind of a pollution which is not there in the EV, but it has a relatively more reliable lifespan than the EVs. After 5 years, we will have a lumps of heaps of batteries pile up, which we will find challenge in disposing of those kind of batteries. Which challenge? That challenge is not there within the hydrogen space. So hydrogen space is going to be a market changer.
And
So
what
you're
will
on
be
the
the
list.
pressure, exact pressure it will require for refilling hydrogen?
Yes, sir. Hydrogen we produce at 34 bar.
Yeah.
Like we are working with NTPC Netra, wherein they have put up two projects. One is in Leh and second is in Delhi, wherein they are converting all of their diesel buses to green hydrogen. As of now, it's still
Yes.
in the nascent stage, initial stage. But yes, it is at 34 bar production and filling up at about 150 bar to 200 bar.
Okay. Okay.
Yes, sir.
Any questions from audience?
Good evening.
Participant?
Uh, Good evening.
Hello, sir.
Yes,
Good
good
evening,
evening.
sir.
Good evening,
Uh,
sir.
uh, it was a very nice presentation from Ashish sir, and I would like to congratulate him for being a part of the Mirai India project. I
Mhm.
wanted to know about how because the Mirai refueling, like it is a compressed hydrogen car. So what was your role in the refueling station? That is
Right,
my first question. And second
right,
question is like there are many technologies like compressed hydrogen as 350 and 700 bars, and the metal hydrate based hydrogen storage and liquid hydrogen storage. So
right.
I came to know that these liquefaction, like the cost of liquefaction, capital cost, as well as the energy consumption, that is 30 to 40% of energy is consumed during the liquefaction. And
True,
this technology is very capital intensive.
true.
So when we hear about the liquid hydrogen, Linda is the first thing that came into our mind. So how
True,
your technology is providing the solution and cost effective solution for the future. And
true.
as you told the boil off losses, you are going to take care in that. How is your plan? So the
Right,
two questions, like
right,
Mirai question, how what was
right,
your role and how
right.
the capital and all these things you are going to manage. Thank you,
Perfectly
sir.
okay. Thank you so much, sir. These are very, very relevant questions. Um, so in the Toyota Mirai project, our role was to develop the hydrogen storage container, which is on triple skin and on lightweight, and that is for the liquid hydrogen storage. So the first thought project, it was on a prototype, and then once they have done all the testing and everything, so now we have a long-term agreement with them for their mass production of hydrogen storage container. Second thing, as you rightly mentioned, that hydrogen is still a lot of people are discussing, not only in India, but in worldwide. But as of now, the shift or the seriousness or the project's viability, that is a big question mark. Big question mark. Why? I always say that before we all most of us use iPhone. So when the iPhone 5 was there, I bought it about 10 years ago. So it was costing about 55, 56,000. And now if we talk about iPhone 16 or iPhone 13, so it's of the same range. So these are all changes which has happened as of now, that semiconductor industry is coming up in India. A lot of people have started developing the chips over here in India during COVID. A lot of incentives were given by government of India to develop those kind of chips. In COVID, we have experienced that the chips was of lot of scarcity. Uh, we bought a remote controlled car, and then they were saying that you can take one key, second key will take about 2 months. So all these thing experience we have experienced. But by the time that all of the chips manufacturing companies started manufacturing chips over here in India, the cost of production, the things have been really, really come down. So same thing which we really need to have, and that is what we are looking at the Government of India initiative, that yes, the Make in India is launched. Because of that, the liquid nitrogen system which we were used to promote, we have experienced that there's a reduction in the pricing. That is a benefit which is for our own country. So similarly, that until and unless these electrolyzers are getting manufactured over here in India, so things will not come to the viable option. That is what, because still we are dependent on somehow or the other, we are dependent on foreign technologies, foreign people and all. So if we really have to self-reliant, so these things has to be actually manufactured over here in India. And once that happen, and that is going to happen, that is what we are very confident of. So once that happens, so I'm sure that we will see a transformational shift into the hydrogen sphere across India. So that is what we are really hopeful. I hope I answered your both questions.
Sir, my second question was regarding the energy required and the economics of your
Yes.
cycle. That I wanted to
Okay.
specifically know about the cycle.
Okay, so basically we are liquefying hydrogen, as you took the name of Linde, you are right. They are into a bigger space. So if I have run my presentation, if you see my product range is from the smaller to mid sector. So similarly for the green hydrogen, we are also liquefying the green hydrogen on the Stirling cycle at minus 253 degrees Celsius. And in that, the cost of production or the cost of electricity is relatively very less. Why? That is something which the study has happened in University of Medicine, in University of Wisconsin in Madison, USA. Whereas in Stirling cycle, the compressed input power and the efficiency, Carnot efficiency is very uh, cost effective. That's what we only take, I would say, 2.5 kilowatt of power for production of 1 liter of liquid. So that is what the economics are. We do not use maximum, we do not have the maximum requirement like in Linde and all those things. Whereas in Linde, the technology is big, that is on air separation unit technology. So they take a relatively higher power than the Stirling technology.
So again, my
Good.
follow-up
Yes.
question is like regarding how do you manage the purity of the hydrogen? Because it is very important that hydrogen to be pure. Otherwise, the mixed gases will be liquefied first. So how do
Correct.
you take care of the hydrogen purity so that the mixed gases will not freeze first and then it will hinder the liquefaction process?
Right. See, as of now, that the hydrogen which is getting produced, so that is through electrolysis process. Our main forte is the liquefaction and then storage. So what the amount of electrolyzer which we choose, so that decides the purity of the hydrogen gas. And once that is fed into our patent technology of cryogenic cryocooler. So the purity which is produced in the electrolysis process, which doesn't have the CH4, which doesn't have the other argon or other oxygen traces or other traces of gases. So based upon that, we liquefy that, and once we liquefy, the it cannot be like that if we are producing at say about 93% of purity, and once we liquefy it will become a 99% of purity. It's not going to happen. But yes, once we liquefy that, so we see a significant, not a very significant, a very small change of the purity level. So that is what we are proud of, that we can liquefy the hydrogen into our patent technology, and then we can store it into our patent storage container. So the purity part, if I talk about PEM, so we can have the purity level up to 99.999%, even 69 also. But in the membrane-free electrolysis, we can, that is what the major USP of our product is, that we can feed any kind of water, whether dirty water or dusty water or any kind of water, and that can be separated through the membrane-free electrolysis, and will produce the desired purity of hydrogen, which is about 96, 97%.
Okay. Thank you. Thank you. Thank you.
Welcome. Welcome. Yeah.
Hello. Good
Yes,
evening,
sir.
sir.
Very good evening,
Am I
sir.
audible?
Mm-hmm.
Yes, sir. Yes, sir.
Yes, sir.
You are audible.
Okay. Okay. Thank you, sir. Sir, I am having very simple question regarding atmosphere. That
Yeah.
hydrogen technology contribute to decarbonization and will be helpful for reducing greenhouse gas emissions. That is
Yeah.
one question. And another question is that what should be the timeline for hydrogen technology adaptation?
Hydrogen technology.
Adaptation.
Yeah. Yes, sir, you are right that green hydrogen absolutely helps in the decarbonization, and that is why that it comes under the Ministry of New and Renewable Energy. and the customers which uh, opt for this solution, so they are entitled for the carbon credit, and they can very well encash those things on in a certain period of time. Coming back to the thing, yes, I have had a couple of meetings at the ministerial level. I still feel that it's only a start, even though NTPC has come up. NTPC has put up two projects, one in Leh and second in Delhi. A lot of people are talking about that, but still I feel that at least 3 years is will take to mature this technology and to make it more, you can say, cost viable solution. As I have given the example of iPhone 5 way back about a decade ago, the costing, and now iPhone 13 or 14. So this there is not significant increase of the pricing just because the technology is mature. The things are getting manufactured over here in India. Apple is coming up, big factory in India. So till that time, those kind of shifts doesn't take place, the viability would be a big question mark.
Okay, sir. As per your consideration, what should
Yeah.
be the technology maturity in percentage, in terms of percentage?
What should be? Can you please repeat?
As per your consideration, what should be the technology maturity in terms of percentage?
Uh, as of now, the I would say that till the time the electrolysis are not getting manufactured over here in India, so the technology is not mature. So that is what the future is. That if we find we have developed technology in and around liquefaction and storage, but yes, we have to really work towards the manufacturing of electrolysis well within our country. And there are many players who are working into it, be it Adani, be it Reliance, so be it Avada. So they are all working towards those towards that goal. So that's not our forte. That we don't want to be with them. We wanted to stick to our core strength, which we have developed over last 7 decades. Recently that the governor of New Mexico, she was also here in the country. So she has chosen some about 17, 18 people who are working in and around hydrogen technology. So I'm glad that I was part of that 18 group member, wherein many of the companies have showcased that this is what they are doing, this is what they are doing, this is what they are doing. So, like Samir project, if all of you are aware that Samir is basically a project which is a joint project of IIT Mumbai and IUSC Delhi and INOX. So, till the time these kind of industry institute collaboration takes place. So now that we are going to experience that the first MRI machine is getting manufactured over here in India, so till the time these kind of industry institute collaboration or gap is not fulfilled, so those things will take time. But I'm sure that now government of India is also very serious and keen towards developing of those, and industries are also adopting. So we are really proud that we have taken couple of technologies from BARC, from Baba Atomic Research Center, wherein we have signed the royalty agreement with them and all those things. So that is what we truly believe in, that the knowledge should not be only contained in the classrooms. It should come out and it should be part of the industries, and professors, the student, the research scholar should take active participation, that whatever they are studying, they are learning. So they should actually see the sunlight of new innovation. Yeah.
Sir,
Yes, sir.
yes. I'm having one question regarding the green hydrogen and gray hydrogen.
Yes.
Nowadays, gray hydrogen is commercially utilized because of its cost, correct?
Correct,
but
correct.
still India is moving towards the green hydrogen mission. As if we compare the hydrogen which is produced from the steam methane reforming, that is SMR process,
Right,
we are getting it is at low cost. But if we
right,
compare the cost of green hydrogen, it is quite high as
right,
compared to SMR. But
right.
then why we are going to shift towards the green hydrogen? Just only because of the decarbonization or
Yes,
any else? And
that
one
is
more
what.
question in line with that, sir.
Yes.
Uh, how we can reduce the cost of that green hydrogen? Is there is any technique or tools so that we can adopt in our research to minimize that cost or to cut off that cost?
So cost is dependent on two factors. As one of the professor has also asked. So costing can only be reduced once we have the manufacturing, whether it's a small one part or something. That is one. On your specific questions of gray hydrogen and green hydrogen, yes, you are very right that gray hydrogen is cost viable and it is used for burning, it is used for this one, many other application. Why we are moving towards green hydrogen? That's all. The fundamental shift is because of the decarbonization. That is what the project which we are putting up in Australia, wherein the iron ore and bauxite mine, aluminium mining is happening. So their vision is that till 2030 they will be net zero, so they will not have any dependency onto their diesel truck. So they will all shift the entire fleet of their trucks from diesel power to green hydrogen power, for which we have given a solution for the storage of green hydrogen. And those are the mining trucks which goes below 3 to 4 kilometer downward. And that is what. And the major thing is decarbonization and the carbon credit. And somehow gray and blue hydrogen, as of now, it's there, but it is going to be replaced with the green hydrogen, and that will only possible once the cost viability of the product is well within the ROI, well within 3 to 5 years or maximum 6 years of the investment. And that day is not very far off. There are many companies, leading companies who are working into day and night to develop those kind of solutions. And that's what we are expecting to be. But still, it will take 3 years at least.
Yeah. Okay, sir. Thanks a lot, sir.
Welcome, sir. Welcome, sir.
Yeah, yeah, yeah. Is there is any question from participants?
Good evening, sir.
Very good evening, sir.
So this is Dr. Shiva. So
Right,
as far
sir.
as this hydrogen is concerned, so mostly we were talking about related to the production. So what future can change in the rocket sciences related to the hydrogen?
Yes, I'm sorry, I don't have answer for this. But yes, we work with ISRO. We work with them for the cryogenic engines, which is basically onto the liquid nitrogen. We have a couple of products, but yes, how it is going to be used for the rocket launching, that's something which I really need to look upon. I'm sorry, I don't have answer as of now, but I'll come
So,
back to you, Dr. Shiva. Yeah,
so thank you so much, sir. If you don't mind,
thank you.
last one more question, sir.
Please, sir,
Sir,
please.
as far as this production of the hydrogen is concerned, or the because since you are practically working on it, so what would be the safety factors need to be at the high risk level, or it's at the you consider as an at the industry level, it is at the high risk or at the medium risk or a low risk?
No, sir, it's absolutely at high risk. Let me tell you that when we have launched our first commercial production way back in 1955 under the brand name of Philips, so our basically hydrogen is also not like an which separated. So hydrogen, we when we launched our first product in 1955, at that point of time, the blanketing of the uh, cold head used to happen with the hydrogen. So whenever our engineers go there and then they have to dissipate the hydrogen into the environment, and then there is a one regenerator which needs to be cleaned. So to save time, what normally people does that they used to clean it with blower and all. So if there is a small trace of hydrogen gas is left out into that regenerator, so it used to catch fire. We used to experience a lot of accidents, burnout, and all those things. So that is what in 1990, so we have come up with that what could be the solution. So that is why now we have shifted the entire blanketing of our cold head is through helium gas, which is absolutely an inert gas, which is very lightweight and all these things. So absolutely, that is what I said in my presentation also, that hydrogen, if it is not handled properly, stored properly, it could turn out to be a bomb. So that is why we have developed a triple skin hydrogen storage container, and we wanted to make sure that if we are using triple skin, that the weight of the container should not be too much, that it cannot be used in either in aviation or in marine or in automobile sector. So that is what we have patent in and around. We have to make sure that the outer shell of that vessel is having a liquid nitrogen. Even if one molecule tries to dissipate from the container, so it will get contained then and there because of it comes into the contact of liquid nitrogen. So that is what we have IP, and it has to be handled in a very decent way. The way we take care of our CNG um, tanks and CNG containers, that we every 3 years we have to do the hydro testing and all those kind of testing. Yeah,
Thank you so much, sir.
pleasure, sir.
Thanks a lot, sir, for your question answer session.
Thank you so much, sir. Thanks a
Yeah,
lot.
yeah, yeah. On behalf of the mechanical department of AIT and all the participants, we express our sincere gratitude for your time, expertise, and contribution to this program, sir.
Thank
We
you
are
so much.
really happy to have you and see you here, sir.
Thanks a lot, sir. Thanks a lot.
Yes,
Pleasure is all mine. And my good wishes to all of you. Let's work together. Let's make our country self-reliant, for which we are
yes,
really.
yes, yes.
Thank you, sir. Thanks a lot.
Thanks a lot. Yes.
Thanks.
We'll wait for 2 minutes for second session. The second session will start within 5 to 10 minutes. We'll have a break.
Datar sir, hello,
Yes,
hello.
yes.
Shall we take 5-10 minute break?
Yeah, sure, sir.
Okay, thank you.
Yeah. Manoj sir.
Yeah, hi, good evening.
Yes. Just a minute.
Yeah.
So I welcome Manoj Mahajan sir into the second session of this FDP. Manoj Mahajan sir is a deputy manager at R&D JBM Green Energy System Private Limited, Gurgaon. He drives R&D strategies, new product development, and compliances with the global safety standards while leading high-performance engineering teams. His work reflects the strong technical leadership, deep material understanding, and proven capability to deliver innovative, cost-effective, and reliable energy storage solutions for hydrogen technology. So I welcome sir for this session.
Yeah.
Yeah.
Hope my voice is audible. It's clear.
Yes, sir. It is clear. Yes, sir.
Yeah.
Yes, sir. Nice to see you, sir.
Yeah, thank you. So first of all, thank you so much for this opportunity. And it's always glad to talk on the technical topics and giving insights. Because most of the time we stays very busy. We stay busy in our, you know, the workload and work pressure. We always stay busy. So this kind of activity, which means from inside, we like to deliver such kind of events or seminars. So where we can contribute um, and demonstrate our experience, where the upcoming, because all I think most of the audience, some will be professionals, some are academic from the students sides. So definitely our experience, because okay, I would like to introduce myself, then I think I will take up further. So I can start.
Yes, sir. Sure.
Okay. So good evening all. Myself Manoj Mahajan. So at present, I'm working in JBM Green, which is the battery division, where we developed high voltage batteries for advanced technologies. And we worked on renewable energy, where energy storage systems, and because JBM is a very big group and we do have our own ecosystems. So starting from generation of energy, which is no doubt renewable only. So renewable energy to energy storage to the road, means for the vehicle. So there are multiple applications, like on BSS we work on uh, energy storage, battery energy storage, giving the energy when it is a peak shaving time and all. So there are multiple projects ongoing. Actually, renewable energy at present, government also having lots of vision for upcoming 2030, 2040, up to 2050. So accordingly, we are also moving, sticking to the government policy and looking at the government vision, how we can mitigate their plans and all. So I'm having 20 plus years of experience in automotive, where I more worked on EVs, electric vehicles. That was my core domain. Its product development from low voltage, like 48 volt, 72 volt, to high voltage system, where the passenger cars from 350 volt, then the bus and trucks, which operates on 650 volt, 800 volts, and energy storage, so up to 1500 volts and all. So it's very nice journey working on such kind of advanced technology. So I think that's it from my side, and I think I can start my presentation. Okay, I'm just sharing the screen. Uh, I hope my screen is
Yes,
visible.
sir. Yes.
Okay, I will turn off the video because maybe the network
Yeah.
may conflict. Okay. Yeah, so coming to the topic, like the hydrogen shift, the next gen energy for automotive sustainability. Yeah. So today's agenda, what I will be more focusing, like hydrogen role in automotive and principles. So where we'll discuss about hydrogen role, how the energy transition has happened from fossil fuel to the renewable energy and all. Basic principles of hydrogen fuel cells vehicles. Then I will more focus on production and development cycle because I think this is the week complete for the hydrogen all different topics where more focus. Some speakers will be more focusing on the hydrogen, its production process and all. Some might have already uh, spoke on the its storage and how the safety and all. So my more focus will be on hydrogen, how it is playing role in automotive and how automotive industry looking this as a next gen fuel. So that there I will be focusing more. So I will talk about how the product development cycle happens from concept to service. Then we'll see market trends and policies. What are the policies which is globally already led and for Indian market? Then what are the OEM strategy and relevant policies and standards, their requirements? So the basic comparison also will discuss how ICE, EV and fuel cell EVs, what are the basic differences and what are the pros and cons of the both technologies and their roadmaps and challenges. So coming to the transition, like we all know the earlier where if you see the last decade means 10 years back or 20 years back, uh, suppose when I'm talking about 20 years back, at that time we never heard about like there will be electric vehicle, means we heard about the development but concept level. We have never seen like realistic on the roads which got productionized or any brand launch their EVs on Indian roads. So now how the transition is happening. Earlier it was a conventional fossil fuel where the energy was getting generated from our fossil fuel like petrol, diesels, and energy was also getting generated with the help of coal and nuclear power plant. But now if you see how the government also focusing on the renewable energy and how the thrust is coming, pushing by some compulsion and all. Because there are multiple things, interesting thing that I will be putting those points as a glance. What is happening in current automotive industry and all. So, like hydrogen is positioned as a next generation energy after EV, and parallel to EV, the development is happening. But because of some constraints and all, it is developed. Some OEMs already launched, but because of its storage infrastructure, ultimately ecosystem. So that complete ecosystem very soon will be formed, and we will see very good numbers in automotive industry by 2030. Then energy transition overflow, like as I already discussed, fossil fuels to hybrid, then electric and hydrogen at present. And sustainability, because sustainability is most important. Like, see, we are working on such an advanced technology. 2 years back, there was a X technology. Just I will give some example. Earlier there was a NMC, then LFP. Very soon solid state batteries will be coming. So like that, technology is evolving so fast, and where manufacturer needs to think because development takes huge cost and time, and where uh, lots of effort needs to be put. So considering all this point and roadmap for the upcoming 10 years, 15 years, 20 years needs to be evaluate as a manufacturer perspective or R&D side perspective. So this is just history. We know that earlier hydrogen experiment has happened, particularly in automotive, like in 80s. Then first fuel cell vehicle in 1966, like the brand, the General Motors Electro van was first fuel cell vehicle. Then later on, there was advancement in fuel cell technology in 1994. Mercedes-Benz also brought their product by Car 1, and 2008 Honda FCX. So these are some launches has happened which were not commercialized, but they launched their product in the market in mass production. If we talk, then there are a Toyota on the top. In upcoming slides, we will talk what are the top OEMs who are really developed their product and good numbers. They could able to launch onto the global market, and very soon it will be on the Indian market also. There are certain requirement related to regulations and all that also will speak in upcoming slide. Yeah, this is basic. We all know, we are more like green hydrogen, where the hydrogen will be getting generated by renewable energy only, like solar cell or wind, from where the energy will be getting generated. Then with the electrolyzer, the hydrogen, the oxygen will be getting separated, and hydrogen will be getting formed, and then its storage to the fuel stations, and at last will be available to us for the automotive as a customer. So this a simple line diagram I shown here. Then this is also very simple, like as a layman to understand how the architecture of this fuel cell vehicle. If you see left side hydrogen fuel, like the fueling station, just let me take the pointer. Yeah. So like the hydrogen is getting filled into the storage tank. I will tell you about what are the constraints, because at what pressure this needs to be stored and how difficult all these things. But this is here we will just talk about the architecture. So the storage tank, then storage tank 2, it is getting fed to the fuel cells, where the oxygen and from the H2 is getting separated, getting released in the tailpipe. And second is uh, the hydrogen, its electricity is getting produced and battery is getting charged. And this battery, the store energy getting converted, there is an inverter which converts the energy and the motor is getting driven. So ultimately, it's from fuel station, tank, then fuel cell stack, battery, motor, then to the wheels. In this, if you see important components, just before I explain, like high pressure tank, fuel cell stack, battery, and their electronics. So here, when the electrochemical reaction happens, and water vapor gets separated and electricity gets generated. High pressure tank, as I said, up to 700 bar for the cars. Actually, for trucks, it's 350 bar and above we are using. Typically, 5 to 7 kg hydrogen in passenger car could able to store at present, and efficiency close to 55 to 60. In that also, somewhere again, it's what technology the OEM is using, where from 40, somewhere it's 50, somewhere 60 also. Using different technology, we could able to achieve the good efficiency. So it is higher than the internal combustion engine, but definitely lower than the EVs. So role of hydrogen in automotive sustainability. So emission reduction, which is because hydrogen significantly reduces automotive emission, because nearly in global 50% of global CO2 emissions from transport sector. So initially force may go on the transport vehicle, where commercial vehicle, that is the target from the government to target those vehicles. So where we can initially focus on good control on the CO2 emissions. And then overcoming EV limitation, like hydrogen provides solution for long haul, heavy duty transport, and cold climate also. There are multiple experiments has happened and still happening. Some pilot projects are happening. Those are also I will give as a case study. Then energy density advantage. We know that hydrogen is having very highest energy density in out of all fuels, and it's lighter and more efficient than batteries for many applications. So sector coupling potential, where hydrogen enables integration across transport, industry, and grid storage, supporting a sustainable energy ecosystem. Uh, this like hydrogen production pathways. At present, we are more focusing on the green fuel only, which is green hydrogen, but gray, which can be produced from the natural gas, CO2 emission high, so which doesn't make sense. The objective, which is our green emission, it is cheap, but it's a high pollution. Then blue, where natural gas plus CCS, it is low CO2 emission, but still it is the objective is not getting served. So the third one, green, which is all the efforts are being applied, and the upcoming means by 2030 the ecosystem will be purely for this particular uh, green hydrogen. Then pink, with the again from electrolysis with the nuclear, it is emission is less, but still it is not viable. So these are the simple steps, exactly what is happening during the production, like production electrolysis process. SMR generates hydrogen gas, then purification, where the impurities needs to be separated. Then compression, like needs to be compressed at 350 to 700 bar. Then storage, stored in the tanks, cryogenic temperature. Distribution via there are multiple at present vessels on the trucks, vessels on the ships, and some pipelines, which is already in the pilot projects. And refilling dispense at the high pressure stations into vehicle, which is this infrastructure. India is very less, but some countries already got good numbers refilling stations, and India also targeting the good numbers, working with NTPC and other agencies, government bodies, you can say. So these are the fuel cells types for the electrolysis. So PM and alkaline, these are the more popular. Out of that, PM is more recommended. PAFC, MCFC, and SOFC. So because if you see the operating temperature, see PM less than 120 degree centigrade, where efficiency also it is 60 degree, 60%, 40% reform fuel. So for our application, this is more effective. Alkaline also, but application wise, if you see, it is military application space and backup power system. PFC also operating, if you see 150 to 200, efficiency is 40% only. Distributed generation, combined heat and power CHP system. And MCFC and SOFC, where temperatures are higher, like we can say cement industry or all, where already heats, high temperature is getting used, so that heat can be utilized, and with that we can serve the purpose. But still, it is not much viable at present. So this is the difference, alkaline and PM, if you see. So it is alkaline electrolyzers are conventional. It's cost effective, but again, energy efficiency and all. If you see for this production, this 4.6 to 4.8 kilowatt hour per Newton meter cube energy consumption, and here it is 4.1 to 4.3 kilowatt hour per Newton meter cube energy consumption. Capital expenditure is higher in PM, which is lower in our conventional method. It is well-established technology, matured already, low initial investment, longer system lifetime, less responsive to variable power inputs. But here, if you see in higher capex, because due to noble metal catalytic, which is very high in cost, a rapid dynamic response to power fluctuation, higher current density and compact design, higher purity hydrogen output, which is close to 99.99 purity. More expensive, which we already seen, and precious metal as needs to be used in this. Yeah. So the right side, you can see the green, hydrogen, gray, pink, and blue, where green is the focus, where produced by electrolysis of water using renewable electricity. So from the solar or wind. It's a clean process. Then India's GSCI certification, Green Hydrogen Certification of India, defines green H2O as a less than 2 kg CO2 per kg H2 produced. Then BEE serves as a nodal authority for certification and monitoring. Mobility application like heavy-duty trucks, intercity buses, and specialty vehicles benefits from quick refilling, long-range pilot projects in India that I've taken as a case study. That also I will show in upcoming slides, where 15 fuel cells and 22 H2 ICE engine across 10 routes are running. So these projects already running in the north at the Ladakh. Then port and industrial mobility, metal handling equipment and port dredge and ground support vehicles at airport and mining equipment. So Green Ports Initiative integrating H2 hubs and Deen Dayal and VOC and Pradeep ports. So this is just we have seen storage and delivery, how the storage at what bar we need to store, like onboard storage, where type 3 metal liner with CFRP, carbon fiber, and type 4 polymer liner with CFRP can operate at, already we know that 350 for the HCV high vehicles and 700 bars for the car for maximum range. And then refueling interface, which is there is standard requirement from the SAE. So the standard nozzle and protocols needs to be followed while installing this refueling stations and their interfaces when connecting with the vehicle, ensuring fast and safe refilling at 350 and 700 bars within 3 to 5 minutes. Tube trailers like compressed gas to 50 bars to 500 bar transported in a tube trailer, suitable for small and medium scale distribution. Liquid hydrogen also stored at the cryogenic storage at minus 253 degrees centigrade, increased density, enabling larger quantities of long distance transport. Usually while shipping and all, this is followed. Future pipeline networks which are already there in pipeline, and safety systems, because the leakage and all that needs to be ensured. There are standard requirement where we have to ensure the safety. So we'll move to the next slide. Yeah, so energy density wise, it is the highest among our all present fuels. So if you see 36.6 kilowatt hour per kg, the energy density. And if you compare with diesel, it's 13 kilowatt hour per kg. So close to 3 times it is higher. And the lithium ion, which is 0.1 to 0.3 kilowatt hour per kg, which is very less. So that's why you might have heard about the energy density is the main factor when you design any EVs. So there you need to focus within the available given space. You need to store a high capacity batteries to get a high range. Otherwise, it's always challenge to get a higher range. Because of energy density constraint, it's a challenge for the automotive industry. Then the range close to 300, 650. Typically, there are different models having a different range. But at present, 300 to 650 range vehicles available in the market. And the fueling time, again, 3 to 5 minutes at the fuel station. Payload preservation, it is, as I said, heavy duty vehicles purpose more focus at present. where hydrogen, the pilot project, which are in India, especially running for heavy duty vehicles. Then in this graph, if you see the energy density which we spoke about, the BEV, if you see, and the FCV, if you see, and the diesel class, if you see, it is very higher energy density for the hydrogen. And if you see efficiency, it is higher than the petrol and diesel, but still lesser than the BEV. Yeah. So this is very interesting topic. You might have heard it or not because it's a standard development cycle. Usually, as a OEM or as a R&D side, when we need to work, we need to follow a very standard product development cycle, where from its concept to its production and service. So how this cycle works, that also we'll discuss in detail. So if you see concept and simulation, actually what happens in product development cycles, requirement comes at a high level, what range we want for our vehicle, then what type of vehicle that will be, what will be the weight of that vehicle, then so many factors needs to be considered because uh, when we need to design a vehicle and to achieve that particular performance, it can be acceleration performance, it can be gradability performance and all. For that, so many inputs needs to be considered, like what will be the air resistance of that vehicle, what will be the rolling resistance of that vehicle. So all these inputs needs to be considered when we do sizing, because based on that only we need to size the motor, then battery sizing, its integration with the simulation and all. We do initial calculation with the simulation. We derive some values, what capacity of motor will require, and how we can achieve that particular performance. Then fuel cell and stack development, again, as I said, uh, because catalyst stack, different fuel cell where catalyst membrane, which is very high cost, and very high cost material needs to be used. So all these things needs to be, and very few are there from where we get these supplies. So many challenges are there while selecting these fuel cells. And again, this hydrogen storage system, because storage is one of the highest safety critical point where we have to ensure, uh, because it's a passenger or it's a commercial. Ultimately, whenever there is a human intervention or human presence with any, so human safety needs to be considered at high level while doing this kind of development. So uses carbon fiber, typically type 4 composite tank, tested for burst pressure. There is some standard. Accordingly, we need to test those shells or tanks, and we need to pass those criteria. So that standard also I have mentioned, even there is one slide in detail. So safety and validation, where we need to test for the hydrogen leak, then its detection for the leak, then crash test, because automotive, it's a dynamic where the vehicle prone to get accident, the accidents chances are there. So how it's a crash worthy, so we need to perform some crash test also. So prevention and refueling cycle and their evaluation. Uh, you might have heard about it, homologation and certification. None of the vehicle in automotive industry can be launched without homologation and certification. There is a regulatory body in India, ARAI, VRD, where the OEM needs to submit their product uh, once, uh, particularly for, if you see, if when we are talking about hydrogen, AS 157 automotive industry standard, this standard falls from some safety compliance requirement. So if you want to launch our vehicle, first of all we have to test in-house very rigorously, and once we are assured, then we submit our vehicle to this test agency. And if our vehicle is complying to this standard requirement, then only OEM can launch their vehicle into the market. So if you see this development cycle for a new project, close to 3 years, 36 months, and some OEMs even takes 48, so 3 to 4 years. It's a complete development cycle to launch any vehicle into the market. Then it's again production and service, clean room vehicle. We'll move to the next slide. Okay. Then vehicle integration and refilling. Here again, hydrogen fuel cell vehicle uses high pressure cylinder rated at 700 bar, um, where existing fuel tanks are getting replaced with this refilling process, which takes 3 to 5 minutes, which is the fastest than the EVs, where we need to wait for a longer hours. There are fast charging also in EV, but those are still not lesser than our fuel filling times, 3 to 5 minutes. Safety and regulation, advanced sensor and valves prevents leaks. These are the safety, because automotive need to comply for functional safety requirement, where for each and every system, how the safety is assured, that needs to be proved to the government bodies or this government agencies like ARAI, when you are launching your product in European market and your American market, where again norms becomes very stringent, and you need to comply or undergo very rigorous testing. Advantage over battery charging, as we said, it's a quick and hydrogen. We are looking for like a commercial where fleet operation, where long distance travel can be done with this, where battery having that limitation at present. EV vehicles having limitations. Then, as I was talking, related to R&D, where we need to go through very rigorous testing, performance and durability, where fuel cell vehicles undergo extensive testing for its performance, durability, and safety. These are all three parameters. Performance, that we need to validate by executing various tests, where range is one of the performance tests, then acceleration, gradability, max speed. These are its performance related tests. Then durability, where we take this vehicle on a torture track. That is also one of the very abuse testing, where uh, our proto vehicle goes on those torture track, and very high G level vehicles are being uh, traveled or run for multiple cycles to check how reliable and durable our product is. Then hydrogen storage integrity, like research focusing on maintaining hydrogen storage, its safety, and preventing for any leakages and all. Then development challenges which are still there, like high cost, particularly its storage and the fuel cell cost, which is very high. I'm particularly talking about automotive part. I'm not talking about the ecosystem. Again, storage, production, which is higher cost, that is again another story. So, like this is the Indian standard which we need to comply, like automotive industry standard AS 157. This is for hydrogen vehicle. And when it comes for the international market, there is a European, United Nation, Commission, where R134. This is the standard which we need to comply. And in this standard, we need to execute certain. What is the objective? Means minimize human harm due to hydrogen related hazard, because these bodies, ARA and VRD, those are formed to ensure a safe product, particularly safe automotive product, to be given to the customer or user. So for that, there there is a society of automotive engineers. So all experts come together, and like you see AIS, this standard, to form this standard, ARA is the government body, but all the experts from different OEM. They are having their bodies who works together and they form this standard. And based on that, this draft copy, after approval of government bodies, even the MORTH, then government bodies like ARAI, then government bodies like Transport Commissioner. After their everybody's approval, only this uh, standard or regulation gets released, and accordingly vehicle needs to be compliant. So it's a alignment of everyone, because here also it's a ecosystem. Then ensuring safe design, as I mentioned, then it's check in this they check the construction and its functional safety, how it is been ensured. Then hydrogen storage safety, how the tanks, then piping is been done or routed into the vehicle. Then leak detection, how it is ensured, what are the leak detection system you have installed in your vehicle. Then crash worthiness, in case of crash, how this system will react uh, when the collision will happen or collision happens, how immediately cutoff wall will take action and it will not propagate. So all this test, or how you ensured all this safety, that gets validated or ensured with this standard. Like fire and explosion, there is a requirement in the case of collision. There should not be explosion or fire. It should be fireproof or explosion proof. How that protection barriers, insulation is being deployed in your particular vehicle. Then electrical safety, like prevent, because it's a high voltage. How the electric shock, how the insulation is ensured, because tank to battery, then battery to motor, then it's a high voltage affair. And anything above 60 volt is a high voltage, with which the human death can happen. That's the safety critical. Life safety comes under that. Then testing and validation, where endurance for running, like as I said, we do bench testing, running multiple cycle, putting on a shakers like vibration shakers and all. We check how whether there is no leakage, how this has been the robust enough, like it will not fail when it goes to the market or when it goes to the customer. So if you see here, this is typical like hydrogen stations, which is the infrastructure shown in this figure. Very the dominating like Japan, South Korea, California, and Europe. There are sufficient numbers. In upcoming slide, we have mentioned the numbers also, because investment is huge. Then competency and capability also one of the factor, where technology and all these things needs to be adopted and to be implemented. Then again, need to future demand and growth, like at, because see, any technology when that needs to be bring in realistic way, then government plays a very important role, because initially they need to give subsidies, uh, because none of the OEM or any manufacturer, they will do charity. Anything has to happen, there should be government support, there should be subsidy, then only it becomes a commercially viable product and comes as a, because when we talk about the scalability, because uh, we might have heard very long back, there is a concept like the vehicle is running on hydrogen, this much range, but unless and until scalability, because that ecosystem, unless and until won't get ready, that will never comes as a commercially viable product. So these are the challenges still are there, but because of government vision, those will be getting achieved. Like why development took time? Because as I said, concept level very long year back, even when Auto Expo used to happen, there also we saw so many top OEM. Tata also demonstrated their bus, but why it has not come on the real market or the production in production. So first, as I said, it's a technological complexity. Like hydrogen vehicle development is slowed because of its complex technology. Now, technology is on board, but again, to develop that ecosystem, for which we need to wait. Uh, like high cost of infrastructure from production to storage, then very limited fueling stations, which delayed this scalability. Then market and demand, low initial demand, market uncertainties. That's why government is taking initiative. Then recent advancement like a green hydrogen production, if it comes, then really it will be a uh, green emission product which will be on the road or on in our market. So how the global strategy and standards are. So if you see the numbers which I was telling there, so global market landscape. So hydrogen vehicle adoption, which has already happened. Hydrogen vehicle population includes 60,000 cars. Out of that, 12,000 close to buses, 8,000 trucks, and 50,000 major chunk, that is forklifts, as of now by 2025. Then regional refueling infrastructure like Japan, Korea, Germany, California, and China, they are having good numbers, good stations they deployed in their countries. Then global hydrogen hotspots, if you see here, like green hydrogen, if you see different color. So like blue, green, red. So these are the hotspots where the investment and infrastructure development is happening. In India also, I have captured in my upcoming slide, that also will speak. So global energy transition, if you see uh, the production, the million tons, again, it's a demand versus the production which we need to deliver. So if you see here in this y-axis, million tons million tons, but at 2020, what was the demand or how much by which way? Refining, chemical production, mobility, transport, power heat, and new industrial application. Different application. How this has been done and how it is estimated. If you see for mobility transport by 2030, major chunk will be for mobility. So for which the hydrogen will be getting produced and will be getting utilized for the mobility application. So 97 metric ton global hydrogen demand in 2030 going grown by 2.5% from 2022. Then clean hydrogen capacity growth from 2020 to 2030 expected from 77 to 48. Then hard to abate hydrogen essential for decarbonizing heavy transport segment. As I mentioned, that uh, commercial vehicle would be first target where we need to, because more maximum pollution at present which is happening with the transport vehicles, because in passenger segment still their penetration has happened like EV penetration and all, but for that big segment conventional was diesel, then CNG has taken, but still there is no clean emission or zero emission. So that will be the major focus for the uh, emission reduction. So this is the global hydrogen vehicle market projection till 2034. So you can see here total market size in billion. Then in that, what is the commercial vehicle and the passenger vehicles? So out of that, if you see here, like from 2.35 billion dollars to 164.5 billion dollars. So like that, the projection is there Up to that, the demand and will be happening. And percentage wise, like compound annual growth rate for hydrogen by 2034, it will be higher, up to 52%. And regional leaders like, as we know that Japan, Korea, and China, they are already dominating or they are ahead, where European and US also putting or having good development, particularly heavy duty vehicle pilots. India again at very beginning stage, but definitely the projects which are at present running, by 2030 we will be having good numbers on the road. Like Japan and Korea, like which is very matured market, where leading passenger fuel cell EVs adoption has already happened because of government subsidies and all. Passenger vehicle, Toyota Mirai and Hyundai Nexo. This Mirai, with Mirai also in India, some pilot projects are happening. Very soon, we will be having some good news from this. Then in Europe, also certain pilot projects also going on. But largely speaking, um, Japan and Korea, those are uh, at very good numbers or big numbers. In India, if you see, like the pilot project which is already running in the north, some vehicles uh, with fuel cell vehicles and some with our combustion engine, hydrogen and combustion engine combination. Leading countries like European Union Hydrogen Bank, $18 million funding. If you see huge investment or huge money is getting invest by the government, whether it is a European government or if it is a Indian government, but a very huge numbers, means huge amount is getting invested by the government. The motto is to push the industry, to motivate the manufacturer, and get the deployment at the earliest. Once the ecosystem is ready, then we will be having good numbers on the road. And if you say the success three pillars: strong demand pull mechanism, infrastructure guarantees, and standardization frameworks, which is same, means the ecosystem needs to be developed on priority. Here also some investment and the finance, how it is been invested, like $30 billion planned hydrogen investment this decade. And this data we have received from up to 2024, and projection is given for 2030. As hydrogen projects mature, the focus is shifting from government funding to private capital. Same thing I mentioned. Initially, government will be putting their money, but the last time it will be privatization. Means OEM needs to take up, and because it's ultimately uh, commercially viable. Because once concept is proven, one the ecosystem is developed for a long term, it will be privatized. So hydrogen up to 2050, how this will be, like this is 25 we are calling is early adoption phase, where hydrogen preliminarily used in refining and chemical industry, very limited for the mobility purpose. By 2030, like because of government vision, definitely mobility will scale up. Heavy duty trucks, fleet vehicles will be getting deployed, and hydrogen cost will also at that time will reach by $2 per kg. Means at present cost is very high, somewhere 250 to 500. Green fuel is very high, 500 to 600 rupee per kg. But by 2030, cost will also go drastically down. Then 2040, it will be transport expansion, very widespread adoption will happen. Then rail, shipping, aviation sector also it will take charge. And production exceed 100 metric ton globally with integrated distribution network across major economies. Then 2050, it will be a very mature hydrogen economy where hydrogen reaches around 7% of final energy demand with a 20 plus metric ton production capacity, fully integrated into energy system with the competitive economics driven by the scale production and technology maturity. Cost declines diverse toward 2050, like declining renewable energy cost projected 65%, up to 65% it will be reduced by 2050. Electrolyzer scale economies and technology improvements, definitely it will be there. Optimizing logistic and distribution system. Market impact and adoption. So hydrogen's market and role. You know that hydrogen fuel cell reduce fossil fuel dependency that everyone wants. That's why the fourth is. Then industry investment, automakers and governments are investing very heavily, like Reliance, uh, investing very huge money for this its development. Then future innovation, R&D also, for R&D also huge money is getting invested because advances in solid state hydrogen storage and advanced material will be improved for safety and efficiency. And renewable energy integration, that is the ultimate aim, to integrate with the renewable energy, because our aim is green hydrogen to be used. Then only it's a zero emission affair. So safety and environmental benefits. So environmental benefits wise, hydrogen vehicles emits only water vapor, significantly reduction in pollution and greenhouse gases during operation. Renewable hydrogen production, like green hydrogen produced from renewable sources, nearly zero life cycle emission, means no emission at all, promoting sustainable energy solution. Safety design features, like as I said, the technology also evolving where robust tank design, uh, leak detection is will be very robust enough. Reliability related to safety will be ensured, and uh, at present means storage and handling is the challenge, but those already taken care, and very soon when it will come to production or SOP, then definitely it will be a safe product to the customer or to the end user. Technology advances, which is continuously it is happening. So advancement in sensors and material enhancement safety standard, because weight is most important when we talk about automotive. You want more mileage, then you need to reduce the weight. But to get more mileage, you need more fuel. Means so it's always contradictory. So to balance this, how you can reduce weight of your, like weight of the battery or weight of the vessels or hydrogen storage tank. If that happens, then definitely we will be having good efficiency or good range out of the product. So like OEM and supplier ecosystem, which we here some example is given, like Tata Motors, leading 16 hydrogen powered trucks trial. Since 2024, it is already initiated. 24 volts validation program is there. Similarly, Ashok Leyland also developing H2 ICE and fuel cell, both the technology, and targeting, as I said, the launch 1824 already started 1.5 years back. So it takes closely 36 to 48 months to bring to the SOP. Powertrain and component supply chain, because supply chain is most important. Most of the components we need to import, how that can be localized. So where we no need to rely on the import. Newer technology pathways like fuel cell EVA and internal combustion also. The OEMs are working on both the technology. Then indigenous manufacturing initiative like localization and all, for which Cummins Tata partnership for hydrogen engines with first units produced in March 24, which is done already. But like when these vehicles will be coming on the road, so that will be the start of production that had to happen. So global partnership and knowledge transfer. Like there is a SOU, MOU has happened, SCCI and H2 Global for export mechanism joint tenders, because Europe and India, both the Technology and Trade Council with 30 plus joint hydrogen R&D proposals are there already. Standard harmonized with UK for safety and certification protocol. Technology transfer arrangement with global OEMs, because here technology transfer plays very main role, because still as I said, competency and technology. So that technology transfers which already our top OEMs already have done. Some things are confidential, but yes, that has happened, and with that only the development has happened or happening. Case study like Tata Motors, as I said, the trial is a part of India's National Green Hydrogen Mission, NGHM. This both fuel cell and hydrogen ICE technology, those are getting tested in a Leh Ladakh. Okay, so 16 hydrogen powered vehicles are there. And it's a 24 months plan where very rigorous validation is happening as per real world duty cycles, means how the load, because a real scenario is different, because if you see vehicle is designed for X payload, but in our India you will never find, you will always find overload. So whether it is a passenger vehicle or whether it is a commercial vehicle, overload is very common. So that's why as per RWUP, means real world usage pattern, the testing is happening. So establish total cost of ownership benchmark compared to diesel equivalents. So back to back vehicles are getting driven to check performance and cost benefit. Optimize hydrogen refilling infrastructure, operation protocol. Here it is green hydrogen they are using, because solar plant from that energy is getting generated, and that is getting converted into green hydrogen, and that is being used for this particular operation or this testing. So in this, who are involved, like Bosch and Cummins, they are always there, because it's an integration. Some domestic OEMs are part of that, and oil making, Indian Oil, BPCL and HPCL, for the infrastructure development, they are working very aggressively. So this is again a case study, hydrogen buses in Leh Ladakh, which is NTPC, led by the NTPC. The location Leh Ladakh. You see here high altitude test. Actually, the main problem, the cold start, because hydrogen is already at the very cryogenic temperature, and the cold start is the problem. So all this validation is happening at high altitude, where oxygen also very lacking, and where temperature also at very low. So at this very worst case scenario, the vehicles are getting validated. So what is the outcome? Successful cold start performance is getting validated in Himalaya, altitude validation, carbon emission, validation of zero emission public transport in remote location. That is the main objective. So this is again say Leh Ladakh, first green hydrogen refilling station, just before I mentioned, 80 kg per day. at altitude of 3,650 meters. 37 vehicles, out of that 15 are fuel cell, 22 are hydrogen ice vehicle, and 9 stations are built to support this activity. 10 routes are identified because uh, identify different route is very simple. To validate the product, like there will be very high gradient, some will be having more like cross country where corrugated potholes will be more. So product needs to be validated at different routes, different road surfaces. National corridor plan, infrastructure development focusing on the strategic national corridor connecting major cities, ports, industrial hubs, with priority given to high traffic freight routes. HDV focus strategy, initial infrastructure development, prioritizing, as I said always, it's a heavy duty vehicle will be the first focus, and for port facilities where centralized refueling can be maximized utilization, operational efficiency. Key players and partnership like Tata Motors, which is already leading a landmark. Very long back, the vehicle has developed 16 hydrogen powered trucks with varying configuration, different duty cycles, 24 months timeline of comprehensive performance, which I said rigorous validation they are doing already. Similarly, Ashok Leyland with hydrogen ice vehicle and FCVs also. Launch to plan in 2027. NTPC established India's first green hydrogen fuel stations at the Leh only, running 5 intra-city FCEV buses and demonstrating hydrogen viability extreme condition. Public-private ecosystem where SECI managing green hydrogen tenders, IOC and Reliance developing hydrogen value chain, uh, Port Authority establishing green hydrogen hub with private partner like SEMCorp. Now, just global OEM, how their strategies are like Toyota's hydrogen innovation. Toyota, they are very advanced. They are far ahead in technology. Hydrogen with second generation Mirai already on the road, and explore hydrogen combustion engine for motorsports. Hyundai hydrogen trucks like Xcient trucks lead global win over 1600 units, which is very good numbers. Upcoming third generation fuel cell system by 2028. So it's a technology which is we say always evolving. So generation 2, 3 will be there. So BMW and Indian OEM like BMW Pilot, iX5, a luxury hydrogen vehicle, Tata Motor and Ashok Leyland develop hydrogen trucks and buses in India. Heavy commercial vehicles like Nikola, Volvo, Daimler Truck focus on hydrogen heavy commercial vehicles, hydrogen corridors in Europe and US. Policies and standards. So like India's green hydrogen missions, which is government has already targeted for 2030 mission. India targets 5 mega metric ton green hydrogen production. So which is very good numbers for which government already assigned the fund, and it's a green hydrogen target is to make Gujarat also having very big chunk of that. Then global hydrogen roadmaps like countries Japan, Europe, US, and China have ambitious hydrogen strategy focusing on vehicles, infrastructure, and logistics. Hydrogen standards, key international standards such as ISO and SAE ensure safety and interoperability in hydrogen technology. Interoperability is nothing but the user will be taking his vehicles to different stations. So uh, initially also I shown you there is standard requirement by SAE like what type of connector the manufacturer with which type of connector manufacturers should manufacture their vehicle, because it's an ecosystem. So any vehicle going to any station, it should able to it should be compatible to their nozzle. So that standardization has already considered in design, and accordingly OEMs are designing their product. This is again NGHM mission, like huge amount, rupees 19,744 crore. Budget has allocated. It's a national green hydrogen mission, under which till 2030 this much money will be getting released by the government in phases. Then 17,490 crores strategic interventions for green hydrogen transition program. Then 1,466 crore allocation of pilot project. So whatever, that's why, means why OEM is taking initiative. Like huge money is getting offered or getting released by the government. 400 crores purely on R&D, innovations, 388 crore other missions, components including governance, skill development, and outreaches. Then to produce this high quantity, green hydrogen target is 20. So enabling industrial decarbonization. So to develop this ecosystem, for that also you might have heard nowadays the BESS, battery energy storage system, renewable energy, very huge, very big tenders are coming, where what government wants, there wherever there are solar plant, wherever there are wind energy, wherever energy is getting generated, that has to be stored and to be utilized for this kind of application. So that is the end goal, for which very big tenders, JBMG also one of that. We also got very good big orders for energy storage system. So just looking at the strategic roadmap, like 2030 is the milestone, where before that infrastructure development has to happen. Then demand will also by that time will be getting generated, or will be there. How the financial mechanism at that time, and standard and regulation also ensuring very safe products are getting delivered to the end user. Yeah, this is the just we are showing here states with hydrogen policies. The blue denotes the states with hydrogen policies and incentives, and the green shows the national program for the hydrogen. So the green hydrogen hubs. So the location, if you see, Gujarat having both, Maharashtra having hydrogen, then Rajasthan, UP, Odisha, then Pradeep Port there only, and Tamil Nadu. This is basic comparison I have shown here. This is basic, but yeah, interesting. Like IC versus EV versus hydrogen. Here you can see energy content. Hydrogen is very high, like close to 120 to 140 megajoule per kg, the energy content, which is very far high as compared to others. So hydrogen has highest energy density, vehicle weight consideration, like EV batteries weight significantly more than the hydrogen tanks. So this is also one of the factor where the high commercial vehicle were putting batteries, because of its energy density is a challenge to meet the high range. So hydrogen will be the one of the best option. Refilling time. EV doesn't make sense where user needs to wait for 45 minutes, 90 minutes. Normal charge takes 5 hours, 6 hours. So that also the constraint which will be getting eliminated by hydrogen. So infrastructure cost is inside that hydrogen stations require significantly higher investment, for which government is supporting. So it will be getting developed soon. Then again, this is hydrogen fuel cell and battery electric vehicle basic comparison. Source is gas. Here is storage battery. It can be NMC, LFP. Refilling time just 3 to 5 minutes. Here it takes 30 minutes to several hours. As I said, normal charge takes 5 hours to 8 hours also. Range is very huge, like 500 to 700. Here it is limited 200 to 400. Range, there are certain other vehicles which use more range, but costs are such a way the user cannot afford. So commercially viable or value for money uh, bringing into the market is always big challenge. Infrastructure, we need hydrogen fueling station, and here the charging stations, which is getting installed at the public location, then malls, and you can find at the petrol stations also. Then emission, here the byproduct is only water vapors, here nothing. So benefit again, hydrogen high density, we already spoke about it, making them ideal for applications requiring high torque and strong performance because it's the electric motor. You can get high torque, 100% torque will be available from the 0 RPM itself. Cold weather performance, hydrogen vehicle operates efficiently in extreme, already validated or validation is happening. And where the batteries are having limitations, battery performs very poor when it goes to below zero. Then again, you need to warm the batteries. Again, energy gets consumed there. So it's again balancing this phenomena is challenge. So modular scalability, like fuel cell stacks, enable scalable solution for multiple vehicle like big buses, trucks, ships, and trains. On-site hydrogen production, like wherever you will be having your renewable energy, hydrogen can be produced on site, and uh, how that's why the ecosystem how it will be. So energy will be getting generated by the renewable in terms of solar or wind. Same near to that place, the hydrogen will be getting produced and then it will be getting transported. Now we'll talk about the challenges and all. Sorry, just a moment. Okay, so see, there we talk about the pros and cons, but disadvantages, the cons, like high platinum cost. It is very higher in cost, around 40% cost takes place for fuel cells around 40 to 60%. And fuel cells require platinum significantly increases the cost. Then leakage risk. We required very robust tanks. Again, tank cost is also very high, 15 to 20%. Sometimes it goes up to 25% also. Like expensive electrolyzers for hydrogen production. Then purity, again, one of the topic, how we are, how it is getting produced. Then transportation issues. Yeah, there were some incident which has happened, which are, which also caused for delay in uh, bringing or launching hydrogen vehicles in market. Like global incident, a notable incident include Norway in 2019. A wall explosion has happened. In Korea, tank rupture happened. 2024, in US, the lab explosion, which were again the setback for this development. Then hydrogen incidents in Norway, Korea, US reveal critical safety. From here, so how this is critical, safety critical. So from that, the development again started, and OEM worked on how we can give very robust product at the end to the market. So safety protocol improvement happened, like incident led to redesign like pressure relief devices, then sensing devices like leak sensors and all, the seals, then shell quality, impacts on safety standards. See, standards are also dynamic. Based on the input, standards are getting amended and it is becoming stringent to have a very reliable and safe product to the customer. Impact and future outlook, like challenges, technical durability challenge like fuel cells, stacks have shorter lifespan compared to diesel engines, require improvements in durability and reliability. Complex system management, like managing thermal and water system in fuel cell is complex, critical for system performance and safety. Infrastructure limitation, like limited hydrogen infrastructure, high operational cost. Then supply chain constraint, uh, uh, platinum shortage, few membrane supplier very limited are there. Tank manufacturer also. So that uh, supply chain development of supply chain, that also evolving and it is taking time, but uh, to meet 2030 plan, that is also happening aggressively. Environmental and market impact. This is like emission reduction benefit. Green hydrogen reduces life cycle emission by 70-90%, eliminating harmful NOx and SOx and particulate emissions. Main important here, job creation. I have put one slide also, which is interesting definitely. How this green hydrogen supports for job growth, how the opportunities are there, like electrolyzer manufacturing, tank supply, fueling station. Ultimately, it's an ecosystem. So everywhere we will require the expertise. Hydrogen vehicle market growth. Hydrogen vehicle market is expected to grow from $70 to 100 billion by 2030, with heavy duty trucks growing at 35% as per CAGR. Okay, customer usage and benefits, superior driving experience. If you drive hydrogen fuel cell vehicle, it's like EV. There will not be noise. It's no vibration, no noise, instant torque, as it's a electric motor, 100% torque is available, very smooth, ideal for long trips, not like EVs, no range anxiety. Then economical and environmental, commercial fleet save fuel cost. Here we have captured some basic technical issues like storage. To store at such a high pressure required very expensive shells. Then fuel cell durability, that is also one of, because it degrades over the time. So very high cost involves. Fuel cell stacks use precious metal like platinum, refueling infrastructure, which is also required very high high cost infra. Energy efficiency, like very few hydrogen refueling stations worldwide, costly infrastructure. Safety concern, hydrogen is highly flammable and leaks easily because of high pressure. Cold start and environmental conditions, it can struggle, but the validation and all which is happening and accordingly it has proven. So this may not be the showstopper or bottleneck. So cost analysis, like fuel cell stacks, as I mentioned, the 40% of the vehicle cost by the cell stack, tank close to 25%, and other components. So you can imagine such a high cost is this fuel cell stack and the tank itself. Then hydrogen cost, if you see in India, gray is very less because it's with the fossil fuel, 200 to 250, blue is 320 to 350. Green is very high, like 550 to 600, and government aim is to bring it down up to 150. In dollar also we saw the global, like $2 per kg means close to 120 rupee, 150. That is the target. Key global player like major companies in hydrogen ecosystem include Ballard Power, Plug Power, Reliance, Linde, Air Liquid, Nail Hydrogen, government pilot project like Toyota, Mirai, Transwet Indian Oil, which is already happening. Jobs. This is interesting. Like you see, 6 lakhs plus opportunity, direct and indirect jobs creation across the hydrogen value chain. So in entire ecosystem, 6 lakhs plus jobs will be available. 1 lakhs plus annual fossil fuel import reduction expected by 2030, strengthening India's energy security and foreign exchange reserve. 15 to 20% estimated boost in manufacturing sector, uh, competitiveness from green hydrogen integration in energy intensive industry. 3,000 megawatt annual electrolyzer manufacturing capacity allotted to 15 firms, creating high skill manufacturing jobs. 5,600 trainees certified in hydrogen related skills through coordinated workflows development program. 8 to 12 billion dollar export potential by 2030 through green hydrogen. 3 hubs, port-based hydrogen hubs established at Deen Dayal, via Chidambaram in Tamil Nadu, Pradeep ports, creating regional economics corridor. 8 lakh crore total investment expected in hydrogen ecosystem. So, as I said, very huge amount is getting invested for this development. 2030, like 5 metric ton per year green hydrogen production targeted under national NGHM mission. 125 gigawatt of dedicated renewable energy capacity. HDV focus like heavy duty vehicle mobility demand concentrated in strategic transport corridor. So heavy duty vehicles and port equipment will be first adoption. NH3 export green ammonia exports to Europe and Asian markets with GSCR certification, leveraging port-based hydrogen hubs in Gujarat for exports purpose. Multi-sector integrated approach across refineries, then our automotive application and all. So India's growth hydrogen production is projected. Last time also we saw how much chunk will be for refinery, what chunk will be for fertilizer, steel industry, mobility, and export. So this is the projection. So 5,000 metric ton will be getting transport expected by 2030. So hydrogen trucks by 2030, hydrogen trucks will become mainstream with over 1,000 fueling stations. That is the plan. Advanced fuel cell technology, fuel cell efficiency will exceed 65% using platinum fuel catalyst and reducing green hydrogen cost close to $2 per kg. Post 2040 hydrogen innovation, hydrogen then fuel ships will be there, green steel, chemical industry, microgrids, and hydrogen aircraft like zero are expected after 2040. Conclusion, complementary mobility solution like hydrogen and electric vehicles work together is a dual cleaner mobility strategy to reduce the ultimate aim is reduce the emission and improve sustainability. Hydrogen is ideal for heavy duty, so application perspective, the more focus will be long range for heavy duty vehicles, while electric vehicles suitable for like city commuting and all urban and passenger travel. Energy independence, hydrogen supports India's goal for energy independence. We don't need to rely for import fossil fuel like petrol and diesel. So it will be our self dependent and by providing a clean and green energy solution. Thank you. That's it from my side.
Thank you. Thank you very much, sir. It was very nice, informative session and very nice presentation from you. Now this is
Thank
the
you so
time
much.
for, yes, yes, sir. Now from participant, is there is any question? We'll take only 2 questions. Is there is any question from participant?
एक रोटी भी कपड़ा निकाली डब्बे में से खाई बोली नहीं कुछ नहीं उसने चाय के साथ. Hello, sir. I have a question.
Yeah, please.
Yes.
Can you please suggest me some methods how to reduce the size of batteries in hydrogen vehicles so that it can be implemented in a more like easy way in transportation, so that we can move towards that research? If you can give us some suggestions or some like clues, hints, so that we can think in that way.
Definitely. At present, are you working on any particular research? Any research is happening?
Yeah, so actually I have my research area in membrane distillation, and that is
Yeah.
very similar to fuel cells. So I am planning to move in fuel cells for hydrogen production.
Okay, so it's a little bit actually technology things, but definitely I can guide on this. I may not directly reply because it's a technology at present, but you can connect with me. I can share my email ID. So where keeping the like confidentiality, how I can support, definitely I will give some solutions.
Oh, that is really uh, like thankful, sir. I'm thankful to you for giving me this opportunity. I'll
Yeah,
definitely
yeah.
connect to you so that we can actually collaborative work in this like field, and I'll be really
Definitely.
happy to work with you.
And somewhere if possible, we'll have a proper NDA where if you really wants to do any like research, it will be a NDA, non-disclosure agreement, and
Yes, sir.
we can assist for the same.
Thank you so much, sir. Thank you. I'll really looking forward to connect with you, sir. Thank you.
Yeah, yeah.
Thank you very much, sir, for your nice and wonderful session, sir.
Thank you. Thank you so
Yes,
much.
yes, sir. We will stop here, sir. Okay, thank you.
Okay. Thank you. Thank you,
Yeah,
team.
yeah.
Thank you so much.
Yeah. I will get back to you, sir, on phone.
Sure, sure.
Yeah, yeah.
Definitely.
Okay, thank you.
Okay. Thanks.
I declare that the session is over for day 3.
Thank you.
Yeah.